Hi everyone, I'm Ella Hipolito and today I'm going to talk about a breakthrough, faster approach of diagnosing diseases, lab on a chip, silicon to sort viruses, DNA, and their nanoscale biological targets. Early disease detection is one of the keys to successful treatments. It's been long imagined for the detection of any disease to be done simply using urine or saliva, for example, at the convenience of home. And this has been the aim of lab on a chip technologies for years now. IBM, in collaboration with Econ School of Medicine at Mount Sinai Hospital, may now have tipped the scales in the technology that could make such at-home tests real. The group has developed a new lab-on-a-chip technology that can, for the first time, separate biological particles to the nanoscale and could help enable physicians to detect diseases such as cancer before symptoms appear. The research team, led by Joshua Smith and Gustavo Solovitsky, has been able to make a 2x2 cm silicon platform. The study appeared in the journal Nature Nanotechnology. The IBM team's results show size-based separation of bioparticles down to 20 nanometers in diameter, a scale that gives access to important particles such as DNA, viruses, and exosomes. It's based on a microfluidic process that uses laminar flow through tiny pores to separate particles based on size. The basis of the IBM team's approach is called deterministic lateral displacement separation technology, which was first developed in 2004. It has area of pillars and the separation occurs because the smaller particles are moving in the direction of the fluid while the larger particles get deflected along the direction of pillar asymmetry. Is analogous to how a pachinko machine works, that it is a machine in which you throw particles and they bounce randomly. But in the nano DLD, the particles bounce to a certain angle due to the set lateral row shift. To test their technology, the researchers targeted exosomes, which are 30 to 100 nanometer structures containing protein and genetic material that are present in many, if not all, biological fluids. Exosomes serve as biomarkers for detecting cancers and other diseases. The area of pillars are made of silicon with gap sizes from 25 to 135 nanometers. Silicon is used because it has high volume manufacturing and its surface chemistry can be altered to mimic natural environment for bioparticles. SiO2 wafers are prepared in bulk by lithography, followed by reactive ion etching to create the nano-sized arrays on the surface. Some of the advantages of this technology is that it can be lower in cost as compared to laboratory testing, it is non-invasive, faster, and requires minimal training. According to theory, when two differently sized particles following the same streamline enter the constriction and negotiate a pose, assuming that the particles do not alter streamlines and do not interact with one another, a particle smaller than the defined critical diameter will remain in the first streamline as its hydrodynamic center is not out with the width of the first streamline. Alternatively, a particle larger than DC is displaced into the next streamline due to its hydrodynamic center being out to the boundary of the first streamline. This action continues at every pose and is termed displacement mode. A patent on an apparatus and method for continuous particle separation was filed by Inglis et al. On 2007 and was granted in 2008. Here, we can see that the disclosure of the technology has been the basis of IBM team's development, including the design and the process, as discussed a while ago. In the Philippines, this technology could be a change maker, especially in the rural and urban poor communities who lack access to proper, immediate, and frequent healthcare. Doctors and hospitals are scarce in these communities. The waived cost of expensive laboratory testing would really help them. One application could include several reactions acting as filters at different levels to ensure selectivity. This technology can change the way we do healthcare and thus can disrupt the way we think about detection diseases, because who would have thought that we can shrink complicated laboratory and hospital processes into a single microchip? Gustavo Solovitsky, program director at IBM Research, said, "When we are ahead of the disease, we usually can address it well, but if the disease is ahead of us, the journey is usually much more difficult." And with that, I end my presentation. Thank you.